My name is Kai Krüger from Mindray Medical. In this talk, we are going to talk about mechanical power, automated monitoring and mechanical ventilation. Let's start with some of the basics about ventilator-induced lung injury. Ventilator-induced lung injury is actually describing the development of acute lung injury that is happening during mechanical ventilation. It's quite obvious that if a ventilator delivers a breath to a patient, it transfers energy to the respiratory system. This energy is actually required to overcome airway resistance and expand the lung and increase the thoracic volume. But a certain part of that energy acts also directly on the lung tissue, and that may cause lung injury. What are the factors for ventilator-induced lung injury? For quite a while, we know that volume and also pressure can cause lung injury as well as atelectatic trauma. So the factors that we were looking into for quite a while are tidal volume by ideal body weight, the driving pressure or applied airway pressures, and the positive and expiratory pressure to avoid atelectatic trauma. There are several other factors that maybe need to take into account as well, which is the breath rate, the resistance of the lung, and also the compliance of the lung. And all of those factors together are taken into account when we talk about calculating mechanical power in mechanical ventilation for a patient. Let's start with some of the physical concepts of power. So what is power? As you see here, the work is the energy associated with the action of a force. And that means it's a product of force and displacement. So a force that is required to displace a body or a tissue is actually the work. The power is the amount of work done per time. In that example here, you can see on the left-hand side, someone going upstairs in 20 seconds. And on the right-hand side, someone going the same amount of stairs up in 10 seconds. So both would create actually the same work, but because on the left-hand side it takes more time, he's doing it for 50% of the power than the person on the right-hand side here. Now, if we look at mechanical ventilation, mechanical power is actually the energy per unit time released to the respiratory system according to the applied tidal volume, the PEEP, the respiratory rate, and also the flow provided. So we can summarize that mechanical power is a summary variable, including all components which can possibly have an effect on ventilator-induced lung injury, which are pressures, volumes, flow, respiratory rate. If we look more into the details how to calculate mechanical power in mechanical ventilation, we see here mechanical power actually consists of the power of inspiration or work of inspiration, which is the volume and the work and the pressure. And the pressure can be divided into the elastic static component, the elastic dynamic component, and the resistant component. Additionally, we take the respiratory rate into the equation and a conversion factor that has been defined. If we look at the formula, you see here volume controlled ventilation as described by Gattinoni et al. That's into respiratory system power. Here the respiratory rate, tidal volume, peak pressure, plateau pressure minus PEEP divided by 2, and the conversion factor. There's a simplified equation that has been published that may be more handy for the daily work at bedside, which actually you can see here. In pressure-controlled ventilation, Becher and al. have published that equation here, which actually takes into account the same conversion factor, respiratory rate and tidal volume again, and looks at the delta inspiratory pressure plus P. So there are different ways to calculate mechanical power and volume and in pressure controlled ventilation. What actually can we do with mechanical power? So there is a publication from an international group that was looking into over 8,000 patients that have been receiving invasive ventilation for at least 48 hours. And they were looking into mortality. And the conclusion here is that high mechanical power ventilation is independently associated with higher in-hospital mortality and several other outcomes in ICU patients receiving invasive ventilation for at least 48 hours. They have found a consistent increase of risk of death with a mechanical power that exceeded 17 joule per minute. Another study was looking into the time-varying intensity of mechanical ventilation and mortality in patients with acute respiratory failure. Here, over 13,000 patients were reviewed. And they also found that a significant increase of death was found to be associated with a daily increment in driving pressure or mechanical power. So both should be carefully monitored during mechanical ventilation. As you see here, the conclusion is the same. If 17 joule per minute is exceeded, the hazard of death increases. We should keep in mind that driving pressure is included as a factor in the mechanical power. So mechanical power includes driving pressure, but it's even including different more factors, so maybe even more accurate in terms of providing a picture of the ventilator-induced lung injury risk. Mechanical power as a measurement has been implemented into a mechanical ventilator, which then provides a constant, permanent display of the mechanical power actually applied during mechanical ventilation. And the study has been done to validate whether that is accurate. So here you see in the abstract the mechanical power is the energy delivered into the respiratory system over time, which we have already discussed. It can be computed as a direct measurement of the inspiratory area by equations. And the aim of that validation study was to investigate the repeatability and accuracy of the measured mechanical power at different peak values compared with the calculated mechanical power. In that study, 50 AS patients were enrolled with a total of 300 measurements. The bias and limits of agreement were described as here, but the measurements were showing that measured and calculated mechanical power were similar in each ventilatory condition, which actually then concludes that the new automated real-time system implemented in the mechanical ventilator was repeatable and accurate compared with the computed one. Here we see Mindray's EA22 high-end ventilator. If we zoom in on the interface, we can actually see different displays for mechanical power. So here the mechanical power is directly displayed, 12.39 joule per minute in this scenario. Also, it was implemented a reference threshold bar, so we can actually set a reference threshold, which is here 17 joule per minute. And you see if the patient is in the intended range, it shows green. If a patient would exceed the range, that number would become red, and also the lung as shown here would actually be becoming red to indicate that there is a risk of ventilator-induced lung injury or injurious ventilator settings. Another value that we have implemented in the SV800 is called mechanical power lung. Mechanical power lung is actually using the calculation for mechanical power, but it is using the esophageal pressure to calculate the pressures that are directly applied to the lung instead of those that are pressurizing the respiratory system. So from that publication, Mechanical Power at a Glance, Simple Surrogate for Volume Controlled Ventilation, one of the citations here is the ideal tool to estimate the role of mechanical power on wheeling would be the availability of esophageal pressure to measure energy that is directly applied to the lung instead of the one that is delivered to the whole respiratory system, which would further help them to get more accurate insights into the settings and the cause for ventilator-induced lung injury. Thank you very much for your time.